In this video, I'll cover about the concept of the backtracking. And if you recall about various strategies which can be followed, which can be used to solve the problem of the any problems related to the algorithms. There are various strategies which involves the divide and conquer strategy, and similarly uh, greedy approach, and as well as uh, backtracking and branch and bound and the dynamic programming and so on. So these are the various strategies which are being involved to solve the problems using the algorithms, that is design and analysis of the algorithms. So coming to the backtracking, so backtracking is one of the most general techniques for searching a set of the solutions or to search for an optimal solution for the given problem. And the name, that is backtracking, was first coined by D.H. Lermer. And the idea behind the backtracking is desired solutions can be expressed in terms of n tuples, that is x1, x2, x3, and so on till xn, where xi are chosen for some set, that is si. And if si equal to mi, then m equal to m1, m2, m3 be the possible kind of the candidates. So some problems can be solved using the backtracking, that is using the exhaustive search. And the exhaustive search technique suggests generating all candidate solutions and then identifying one with the desired property. And backtracking is a more intelligent variation of this approach. The principal idea is to construct the solutions one component at a time and evaluate such partially constructed candidates using the following ways. That is, if a partially constructed solution can be developed further without violating the problem's constraints, it is done by taking the first remaining legitimate option for the next component. If there is no legitimate option for the next component, no alternatives for any remaining component need to be considered. That is what the concept of the backtracking has been involved. And in this case, the algorithm backtracks to replace the last component of the partially constructed solution with its next option. That is, the brute force approach has been involved to find all the possible solutions, out of which we'll be finding the optimal solution. So forming all candidates and evaluate each one and saving the optimum one is the concept of the brute force approach which has been involved. And coming to the backtracking, that is, it yields the same answer with far fewer more than m trials, rather than finding all the solutions using the brute force method. We are restricting such that further, if you go further ahead, you may not get the solution. In such cases, backtrack and find another path which may lead to the solution. Its basic idea is to build up the solution vector one component at a time and to use modified criterion function, that is P1 of x1 comma x2 comma xi, which is sometimes called as the bounding function, to test whether the vector being formed has any chance of success. The major advantage of using the backtracking is that if it is realized that the partial vector, that is x1, x2, x3, and so on, can in no way lead to the optimum solution, then mi plus 1 and so on till mn possible test vectors can be ignored entirely. So rather than finding all the solutions which may not lead to the optimal solution or which even not been considered in the solution set, then in such cases you can draw that kind of the items. So basically, when used about the backtracking, the principal idea is to construct the solutions one component at a time, and evaluate such partially constructed candidates using the following ways. That is, if a partial constructed solution can be developed further without violating the problem's constraints. What are the constraints? That is implicit constraint and similarly explicit constraint that will be discussed in the next further coming slides. And if it is done by taking the first remaining legitimate option for the next component. If there is no legitimate option for the next component, no alternatives for the remaining component need to be considered. So in this case, the algorithm backtracks to replace the last component of partially constructed solution with its next option. So here the backtracking is the general algorithm for solving some computational problems. Most notably, that is constraint satisfaction problems that incrementally builds the candidates to the solutions and abandons the candidates backtracks as soon as it determines that the candidate cannot be completed to a reasonable solution. Backtracking algorithm is used in various applications, including that is n-queens problem, maze solving problems, and search for all the Hamiltonian paths in the given graph. So like take for example, what is the difference between the brute force method and as well as the backtracking method? So within the case of the brute force method, you'll be finding all possible solutions. But unlike in the case of the unlike in the case of the backtracking, so if you are choosing a particular path and if it leads to the optimal solution, then you can go further ahead. And if at any level, if you do by taking that kind of the item or that kind of the option, if it does not lead to the solution, then you don't have to go further levels. You can backtrack and find the other path which may lead to the possible solution. That is what the backtracking concept is being involved. So I'll give an example of the concept of the backtracking by providing, like take for example, consider the problem. That is given the letters, that is A, comma B, comma C. The three letters are being given, and you need to arrange these three letters in such a way that C cannot be beside A. That is, the letter C cannot be beside the letter A. Consider this kind of the problem. Then in such cases, that is using the brute force method. So using the brute force method, and also explain about using the backtracking method. So within the brute force method, we start from the root and by considering A, because three letters can be arranged. So we take the first letter to be equal to A. And in the next scenario, I take the next letter to be equal to B. And in the next scenario, I take the letter that is C. And when I take A as the first letter, the next possible letters that can be present are that is B and similarly C. Similarly, when I take the first letter as B, I can take A as the next letter, or I can take, that is, C as the next letter. Similarly, if I take A, B, and the next letter should be equal to, that is C, because only 3 letters are being allowed. I'm not considering the other problem like C cannot be beside A. I'm finding out all the possible solutions where we can arrange these 3 letters. And if I take the first letter as C, the second letter, first letter as A, the second letter as C, the third letter that can be present is B. Similarly, B, A, C can be present, and so B, C, A. And if I take the C as the first letter, then it can be either B or it can, A, or it can be either B in the next solutions. And similarly, if I take C, A, the only letter is B, and C, B, the letter that will be present is equal to A. This is called as a state space tree. State space tree diagram. And here, when you consider about the backtracking, so what are the possible solutions of your brute force method? That is, you can have A, comma B, comma C, and similarly A, comma C, comma B. That is A, B, C, A, C, B, and the next one, that is B, A, C, and the next one is B, C, A, C, A, B, C, B, A. These are the all solutions that can be arranged given the 3 letters. And out of which, what is the problem that is being given? The problem is C cannot be beside A. That is, here, if you consider this is not the feasible solution, it is not the solution, and this is also not the solution, and this is also not the solution due to the reason like C is beside A, and C is beside A. This is not the solution, and these are the 2 solutions. That is, the solutions are A, comma B, comma C, and the next one is C, comma B, comma A, satisfying the problem. That is, C cannot be A. And how this concept is being implemented using the backtracking concept? Take the same scenario. That is, we start at the top level with the top level, and what are the possible paths that have been available? We can take the first letter as B, and we can take the first letter as equal to A. When you take the first letter as A, and what will be the next letter? The next letter, can I say C? C cannot be placed because C cannot be beside A. So C should not be taken. That is how we are restricting. But according to this case, if I take A and similarly B, and similarly to the next level, that is C. So this led to the one of the optimal solution. And the next one is the other path is take A, and what about the next path? That is C. If I take this particular path, we cannot go to the solution. What is the problem? That is, C cannot be beside A. That is a constraint. So if I place C in this kind of order, C is being placed beside A, and that is a purpose where we cannot go further ahead. You don't have to go further ahead and stop it and move to the backtrack. That is, go back and find the other path. That is B. So if I place B over here, and similarly, what possible paths can be taken? You can take either A or you can take either C. If I take A, then in such cases C will be present here, and if I draw here, according to this case, A and similarly C, these are beside. So backtrack. You cannot take this as the solution. And similarly here, if you take C, then A will be present. So here C and A are beside. This is not the solution. Go back, and similarly the next path will be equal to, that is, take the letter C. If I take C, then can I take A? I cannot take A because both the things C and A should not be beside. And what is the other path? That is, you can take B. And when you take B, the only letter that is being left out is A. And that is the purpose where there are 2 solutions. So here, according to this case, that is A, comma B, comma C. and similarly C comma B comma A are the possible solutions. You are not going further ahead when you find that it is not the legitimate solution. If it is not the legitimate solution, then you don't have to go into mi plus 1 and similarly mi plus 2 till mm. Here I've considered only the 3 letters. But if you take more than something like more letters are being present, then in such cases, rather than going using the brute force method and then later on finding what are the possible solutions, instead, if at any case, if the constraint is not being satisfied, constraint according to this case is that is A and C should not be beside. So according to this case, these two letters are beside. And that is a purpose where you cannot go further ahead. You don't have to go further ahead. Backtrack and take the other path and find by taking this particular path what are the options that you have and out of which what is the feasible one, what is a constraint that is being satisfied. The constraint is being satisfied, then in such cases take that kind of the solution into the solution set. If not, backtrack and find the other possible solutions. This is how we can solve the problem of the backtracking using the concept of the backtracking. So backtracking is an algorithm technique whose goal is to use the brute force to find all solutions to a problem. And it entails gradually compiling a set of all possible solutions. Because a problem will have the constraints, solutions that do not meet them will be removed. That is, a bounding function is being applied. And it finds a solution by building a solution step by step, increasing levels over time using recursive calling. A search tree known as the state search tree. That is, here we are using the state space tree diagram, is used to find these solutions. Each branch in a state space tree represents a variable, and each level represents a kind of the solution. So here, if you observe this kind of the component of the backtracking, so here it also involves the concept of the brute force method. But unlike in the case of the brute force method, rather than finding all possible solutions, we'll be finding the solution in such a way that if it is a legitimate option that you have considered and the constraints are being satisfied, then you can go ahead. Else, you can backtrack and then find any other kind of the possible paths which are being available. That is how the backtracking concept is being involved. And here, when you need to solve the concept of the backtracking, that is, the backtracking algorithm uses the concept of the DFS. Backtracking concept uses the DFS concept, that is, depth first method. So when the algorithm begins to explore the solutions, the abounding function is applied so that the algorithm can determine whether the proposed solution satisfies the constraints, and if it does, then it will keep on looking for the next levels. If it does not satisfy, that is, the constraints are not being satisfied, then the branch is removed and the algorithm returns to the previous level. So if you consider about the constraints in the backtracking, that is, solutions must satisfy the constraints. There are two types of the constraints, that is backtracking and explicit constraints and implicit constraints. So if you consider the explicit constraints, which indicates the rules that restrict each xi on to take on values only from the given set. That is, xi can be greater than or equal to 0, or that is si equal to all negative, non-negative real numbers. Xi can be equal to 0 or equal to 1. Then it can be represented as si equal to 0 comma 1, and similarly li xi ranges between the lower bound and similarly upper bound, which has been represented by si equal to a. That is, it can be between the range li and similarly ui, which stands for the lower bound and similarly upper bound. So all tuples satisfying the explicit constraints define a possible solution space for I. where I indicates it is a problem instance. That is related to your explicit constraints. And coming to the implicit constraints, these are the rules that determine which of the tuples in the solution space of or satisfy the criterion function. Thus, implicit constraint describes the way in which xi must relate to each other. So in any backtracking algorithm, the algorithm seeks a path to a feasible solution that includes some intermediate checkpoints. If the checkpoints do not lead to a viable solution, the problem can return to the checkpoints and take another path to find a solution. Backtracking is a class of algorithms for finding the solutions to some computational problems, notably the constraint satisfaction problems that incrementally builds a candidate to the solutions and abandons a candidate as soon as it determines the candidate cannot possibly be completed to a viable solution. The classic example of using the backtracking is the 8 queens puzzle, that is 8 queens problem, that asks for all arrangements of the 8 chess queens on the standard chessboard so that no two queens are under attack. In the common, the backtracking approach, the partial candidates are the arrangements of the k queens in the first k rows of the board, all in different rows and columns. Any partial solution that contains two mutually attacking queens can be abandoned. The bounding function here in this case is no two queens are to be placed in the same row or in the same column. So backtracking can be applied only for the problems which admit the concept of the partial candidate solution and a relatively quick test of whether it can be the possibly be completed to a valid solution. It is useless, for example, for locating a given value in an unordered table. When it is applicable, however, backtracking is often much faster as compared with the brute force method due to the reason like it enumerates all complete candidate solutions. And also since it can eliminate many candidates with a single test. That's how the backtracking concept is being implemented. And similarly, the constraints, as I mentioned, there are two constraints like explicit constraint and as well as the implicit constraint. So within the case of the explicit constraint, like say for example, SI equal to, for the 8 queens problem. So for the 8 queens problem, that is SI equal to 1, 2, 3, 4, because what are the possible items that can be taken? It is ranging from 1 to 8. That is, there are 8 queens which are present. And similarly, so the solution space consists of 8 tuples, that is 8 to the power of 8 tuples, the possible combinations. And implicit constraints, that is no two x's can be the same. That is, by this, the solution space can be reduced from 8 to the power of 8 to the 8 factorial. And no two queens can be on the same diagonal. That is what the 8 queens problem is being involved. So here, when you take the concept of the components of the backtracking, the components of the backtracking, which involves, that is decision tree, and similarly the recursive approach, and the next one, that is backtracking step. So these are the components of the backtracking. So when you consider about the decision tree, that is a backtracking algorithm explores a problem by building a decision tree. Each node in the tree represents a decision or choice that can be made, and each branch represents the consequences of that choice. And coming to the recursive approach, That is, backtracking uses the recursion to explore the decision tree. At each step, the algorithm makes a choice and then recursively tries to solve the smaller problem that results from that choice. And coming to the backtracking step, that is, if the current path or choice does not lead to a valid or the optimal solution, the algorithm backtracks by undoing the last decision and tries a different path. This step ensures that all possible options are explored until the solution is found. That is how we can say about the components which are being included within the backtracking. And how this kind of, like take for example, when to use the backtracking concept. So when we have the multiple choices, then we make the decision from the available choices by satisfying the respective constraints. And a piece of sufficient information is not available to make the best choice. So we use the backtracking strategy to try out all the possible solutions. So when initially, if we do not know whether this particular path leads to the solution or not, we'll be finding the best choice. And if it is not the solution, or which does not lead to the optimal solution, or which does not satisfy the constraint, then backtrack and try out for all other possible paths which have been available, which may lead to the solution. As a part of the example which I've said in your previous part, that is, here if you take A comma B comma C as the three letters, then in such cases, no to adjust, here C and A should not be present beside. Then in such cases, we start from the by taking the option to be equal to A, and then we have moved to the next levels, and we are filtering out, or we are removing the branch where if it contains C and A as the beside letters. So each decision leads to a new set of the choices. Then again, we backtrack to make the new decisions. So in this case, we need to use the backtracking strategy. In which scenarios the backtracking concept is to be implemented. When we are starting at the from root level, that is at this initial position, and we do not know whether this path may lead to the optimal solution or that path, or whatever the paths which have been available. In such cases, start initially and go on to the depth and find whether it leads to the solution. And if it does not lead to the solution, backtrack and simply go on. Like take for example, if you consider the G Polarity Engineering College, where the new person has entered. That is, here the person enters from the main gate and he goes on straight and finds the department to be equal to something like CSC department. So if the person does not know, of course, forget about the security and forget about the other persons which are being involved. I'm just trying with the concept of the backtrack. So he first moves over to the cafeteria or the exam section, and similarly here he finds that this is not the CSC department, and come back and then take the other paths. Like take for example, if you go to the left, we get CSC department. If you go straight, we go the exam section, and similarly ECS exam section. And if we move to the right, assume like we get the ECS department. So we are initially starting and then move straight, and exam section has been formed. So that is not matched. That is backtracking. That is not the CSC department. So come back and then find the other path. That is move left or move right. If you move left, then the solution has been found. If you move right, then ECS department. Come back and then find the other path. This is how we'll be solving the problem of the backtracking strategy. So here we have also learned about the state space tree diagram. So what is a state space tree? That is a space state tree is a tree representing all possible states. That is a solution or the non-solution of the problem, from the root as the initial state to the leaf as the terminal state. That is, we are starting from the root and we are reaching to the depth and so on, and find whether it leads to the optimal solution or not. If it does not lead to the optimal solution, then backtrack and find the other path which may lead to the solution. Even if it does not find the solution, backtrack and then find the other paths which have been available. Then if it leads to the solution, then take that into the solution set. And if it does not, then move, backtrack, and then find the other kind of the paths which have been done. So this is how we can introduce about the concept of the backtrack.